Have you ever just stared at a carton of milk or maybe a can of soup on your shelf and thought, how in the world can this last for months, sometimes even years without going bad? Well, it's not magic, but it is some seriously impressive science. All right, let's get into it and unpack the fascinating world of food sterilization. I mean, really think about that for a second. We're all programmed to rush fresh milk into the fridge, right? But this one can just hang out in the pantry. What is going on there? The answer is a single, incredibly powerful process that totally transformed how we store and eat food. And that process, of course, is sterilization. But here's a really key thing to understand. When we're talking about the food industry, sterilized doesn't actually mean 100% absolutely zero microbes. See, to get to that level of sterility, you'd have to use so much heat it would just destroy the food's taste and all its nutritional value. So instead, the goal is to eliminate enough of them to make the product totally safe and stable at room temperature. It's all about hitting that perfect sweet spot. So here's our game plan for today. We're going to start with the classic way of doing things, sterilizing food right there in the can. Then we'll jump into the UHT revolution, which kind of flipped the whole process on its head. After that, we'll tackle the incredibly tricky challenge of packaging. And finally, we'll see what it takes to keep these massive systems running safely day in and day out. All right, let's kick things off with the method that just makes the most sense at first glance. You put the food in a container, you seal it up tight, and then you heat the whole shebang. You can think of it like a pressure cooker, just on a massive industrial scale. This is really where it all started. These machines are called retorts, or you might hear them called autoclaves. Basically, giant cages full of cans are loaded into this big pressurized tank. Then, high-temperature steam gets pumped in to sterilize everything inside. But here's a really cool detail. When the cans are being cooled down with water, compressed air is pumped in at the exact same time. Why? Well, it's to keep the pressure outside the can equal to the pressure inside, which stops the cans from buckling or even bursting. It's a pretty simple idea, but absolutely crucial. Now, even with this in-container method, you've got two main ways to go. Over on the left, you have the batch sterilizers we were just talking about. The great thing about them is their flexibility. You can stick all different size cans in there, but they're slow and they take a lot of manual labor to operate. Then on the right, you have the continuous sterilizers. These things are beasts, built for huge production lines. Cans are always moving through different heating and cooling zones, and they're even rotated to stir up the food inside and make the heat transfer faster. So you can see the trade-off, right? Batch systems give you flexibility, but continuous systems give you incredible speed and scale, as long as you're only using one specific can size. But what if you could just flip the entire process around? Instead of sterilizing the container with the food already inside, what if you sterilize the food first and then put it into an already sterile package? Well, that is the UHT revolution, and let me tell you, it completely changed the game. UHT stands for ultra-high temperature, and we're talking incredibly high heat, like around 140 degrees Celsius, but for a ridiculously short amount of time, sometimes just a couple of seconds. This high-heat, short-time method is just brilliant. It's enough to get the job done, to make the food commercially sterile, but it's so fast that it causes way fewer of those unwanted chemical changes to the food's flavor, its color, and its nutrients compared to that long, slow cook inside a can. So what does this journey actually look like for, say, that carton of milk? It all happens in this continuous, super fast flow. The raw milk is first preheated, often using heat that's recovered from the cooling process, very efficient. Then, boom, it hits the final heating section for that intense, super brief blast up to 140 degrees. It's held at that peak temperature for just seconds before it's rapidly cooled back down, all ready for packaging. It's this incredibly precise and controlled dance of temperature, and it's all happening on the move. Okay, but how do you actually get that crazy fast UHT blast of heat? Well, there are two main ways to do it, and they both have major pros and cons. With indirect heating, the food flows through pipes that are heated from the outside. It works, it's efficient, but those hot surfaces can get all gunked up with burnt-on food. It's a problem called fouling. Then there's direct heating. This is where you inject super pure culinary-grade steam right into the product. It heats it up almost instantly, and you don't get any fouling. But it's way more complex, more expensive, and it temporarily adds water to the product, so you then have to flash off that exact amount of water in a vacuum chamber just moments later. So, you've done it. You have this perfectly sterile UHT-treated product. Awesome. But now you have a massive new problem. How on earth do you get it into a package without a single stray microbe from the air getting in and ruining everything? This, my friends, is the aseptic packaging challenge, and you could argue it's even harder than the sterilization part. To actually pull this off, manufacturers have to live by 5 golden rules, and there is absolutely zero room for error. Every single component, the container itself, the lid, the filling machine, all of it has to be sterilized and then kept inside a completely sterile bubble until that package is sealed up tight. If just one stray microbe gets in at any point in this chain, the whole process is ruined. It's a high-tech, high-stakes operation with zero tolerance for mistakes. So, how do you sterilize the packaging materials themselves? Well, there are a few go-to methods. You can use high-pressure saturated steam, which is super reliable but needs a pressure chamber. Dry heat can work, but you need some seriously high temperatures. A really common method, especially for those cartons we've been talking about, is a 1-2 punch of hydrogen peroxide and heat. The packaging material gets sprayed with or dipped in peroxide, and then it's heated up. This does 2 things. It activates the sterilizing power of the peroxide, and it evaporates it completely so none of it gets into the food. And this perfectly explains the technology inside that shelf-stable milk carton we started with. It's not just cardboard, not even close. It's a really sophisticated multi-layer laminate. You've got the paperboard for structure, then layers of polyethylene on the inside and outside to make it waterproof, and sandwiched in between is a super thin layer of aluminum foil. That foil is the secret weapon. It acts as a powerful barrier against both oxygen and light, which are 2 of the biggest enemies of shelf life. Okay, so we've got the process and we've got the packaging, but these are incredibly complex, high-performance systems. Keeping them running perfectly day in and day out is a science all on its own. It takes constant care and meticulous maintenance. Success here really hinges on several critical factors. It all starts with the raw product itself. For UHT to work well, you absolutely have to start with the highest quality milk. Then there's the equipment. The gaskets that seal the plates in a heat exchanger, for example, can't just be any old rubber. They have to be made of sophisticated materials like EPDM that can handle the intense heat and pressure without failing. And finally, the overall hygiene of the entire plant has to be absolutely impeccable to prevent any chance of recontamination. This quote right here really just sums up the whole challenge perfectly. Look, building a machine that can heat a liquid up to 140 degrees is one thing. But designing and running a system that can then flawlessly package that sterile liquid thousands of times an hour without a single contamination event, that is the true engineering marvel here. Most spoilage in these products doesn't happen during sterilization. It happens right here, at that final critical packaging step. So the next time you grab a shelf-stable product, you'll know the incredible journey of heat, pressure, and precision that it took to get to you. We have truly mastered heat as a tool for preserving our food. And it kind of makes you wonder, what's next? What new technologies will define the future of keeping our food safe, nutritious, and fresh?